the first man on stage.
Hello, thank you for the introduction. I wish everybody a nice evening here. I will start with presenting how we develop a virtual simulation and testing system for automotive applications based on a gaming engine. It's called Ostrex. And this development has been done entirely in Prague. It started here, and it's been developed here. And it's already gained momentum in other sites of Valeo that are into ADAS development around the world. So first, something about me. I also come from Czech Technical University. I studied control engineering. That's not directly related to development, but I think most of us end up in software programming in the end, anyway. And I'm Jan Valeo 4 years ago. I'm in the Department of Vision Systems. Our most interest is in the surround view cameras and parking cameras, which means the cameras that cover the nearest range around the car. And I'm from software tooling and test infrastructure. I'm also lead developer of this simulation system. So just a little louder. So I split the presentation into 3 parts. First, some generic things about testing in automotive applications, then on engineering of our 3D simulation system, Ostrex, and then some examples of sensor model development if we get enough time. So first, about testing. Testing is, of course, the most important thing in automotive development. It comes from me, from testing department, so you should believe me. Many tests are executed during the product lifecycle. It means the software releases are continuously updated. If you buy a car and you go for regular checks, it's always updated, or very often it's updated. The software, you don't even know about this. But during the lifetime of the project, you continuously deliver to the car manufacturer. So the software testing and software development for a specific project can take 8 years, and during all this time, it's being continuously tested. There are, of course, many levels of testing, like you can imagine that some electrical and environmental tests will be done. There's testing of the software on the basic unit tests of classic software engineering approaches. But our interest here is the system testing. This testing covers the end user function, which is a function that's perceived by the driver in the end. So it means like you press button, the car parks automatically, or automatic braking. So it's really the top level function that's perceived by the end customer, by drivers. We have basically 2 ways how to test such functions at this point in time. So it's either the vehicle testing, that we have actual vehicles, actual test drivers performing the maneuvers, or we use test bench testing, where we take our system and simulate it on a test bench in an office environment, where we have to simulate the inputs and follow the outputs of the system. There is also, you could know, software in loop testing, but it's not very practical for several reasons. Main being the dependency on hardware. As the things evolve, more and more functions is carried over to specialized hardware chips in the electronic control units. So this is something we cannot anymore test, so, at least in ADAS applications. Here is a brief comparison between car testing and bench testing. I guess most of you can easily guess the plus and minuses of both approaches. So of course, this is very time consuming, it's very expensive, you need car, you need many people, you need place where to do it. And of course, the bench testing, being the simulation, of course, we develop very good simulations, but still it's only a simulation. So customer will not take this test as a valid or as an end test for production release or so far. But it's very, very useful for our internal testing and for internal development. It's also very useful for car variant testing. It means our one product is typically used by a manufacturer, but in many different car lines or car styles. And we, of course, do not have the physical cars of any possible variant or any model. So this is very useful to simulate the different car variants on a PC-based testing. For instance, this is the latest E-Class that I have in my example today. And this car only has like 4 car variants for us. It can be different styling, different bumpers, it can be of different height. So it seems like it's the same car, but even this is 4 car variants for our product. So really, there are many variants, even more than even one would guess. I've already started on the example project. It's a Daimler parking unit. It went into market in 2016, so it's already quite old. This electronic control unit is used for automated parking, for emergency braking, and also for surround view system, which means that the cameras around the car match an image and you can see on the display on the driver stack. As its sensors, it is 4 fisheye cameras and 12 ultrasonic sensors. And this ECU actively drives the vehicle during the parking maneuver or during the braking maneuver when it detects some obstacle in the way. So for testing, this means that the simulation and test environment has to follow the orders from the ECU, which means when I'm in the middle of parking maneuver, the ECU tries to steer, and the simulation has to reflect this adequately. So it's no longer possible to, let's say, make a pre-recorded videos or pre-recorded races that play back to the hardware device and you see the reactions, because we have to also react on what the ECU or the hardware device commands. This is the electronic control unit in question. It has 4 cameras that are in front of the car, rear of the car, and in the side mirrors. It has 12 ultrasonic sensors, and it also expects some vehicle data. So all these blue lines is what our simulation has to provide to the ECU to keep it thinking that it's driving in a real car. On the other way, our simulation has to follow these control signals. Among others, this request for setting steering angle, requested gear change, requested speed of travel, and maybe some more. It also has a video output, but it's only for this driver overview or for test overview. It's not considered in our system here. So when need for such testing occurred, we decided to go to develop our own simulation system. Well, we tried to purchase it first, but in the end it was not very successful, so we started in-house development some 3 years ago, and through some, let's say, proof of concept and some intermediate versions, we came to this. We call it Vostrex. And I go through some requirements or some functions on this that come to mind. We, of course, for perception or for simulating the environment, we have to simulate the environment. We have to simulate the vehicle movement, like kinematic and dynamic properties. We have to simulate the sensors that will be sent to the ECU as an emulated data. For this, we here simulate mostly ultrasonic sensors and fisheye cameras. We also have other sensors in the range that we are able to simulate, but today we only cover these 2. The biggest and most important requirement is the real-time performance that we have to generate the data with, because there's a real piece of hardware in the loop, and it of course expects the real-time happening. We can't slow it down or speed it up. Of course, we have to think about scalability to be powerful enough with our performance requirements and to take advantage of modern PCs. Visual quality is not much of an interest to us. We just need to make the obstacles of the sensor responses good enough for the ECU to perceive what we want to show or what we want to inject to the ECU. We are not going for the biggest level of realism, like probably many of you are in the computer vision and neural networks and stuff like this, so we are quite the opposite. We go for just the bare minimum that's needed for the ECU to recognize the pedestrian or parking line. We of course would like to have it beautiful, but the performance requirements are more important here. So at the beginning we had of course to select some 3D engine. We went through the most obvious choices and some not so obvious, and the winner we chose was engine called Euro 3D. I don't know if Any of you ever heard of this or use this? No? So it's not very famous. The advantages was it's open software, and it was, in my opinion, a very, very nice coding style in C++. I was actually surprised that such things can be done in C++. At this time, we chose it. I mean, it's 2016. It had a very active community, and it was readily available for me. To be honest, purchasing something in a corporation is not very quick process. So if I can download it and use it, it's the best. So this is one plus two that should not be probably discussed too openly. Disadvantages is the same as open source software. So recently the main developer left, and we are not quite sure about the future, but okay, we have it, what we got, and we can improve it ourselves always. It's open source. So the assets or the 3D models database is very, very basic, and nowhere near compared to Unity or something, and the visual quality is also basic. So the other obvious reason would be Unity or Unreal, that are really stunningly looking and have huge fan bases and huge databases of assets or 3D models. But first of all, you have to purchase it, which would slow me down. And second of all, in case of Unity, I do not know the details, but I understood you can manipulate it through some kind of .NET scripting. So I was very cautious about real-time performance and predictable timing, which was a very strong requirement. And Unreal Engine had licensing conditions that they want 10% of revenue for a project, which would be quite a lot if you're not developing a game, you're developing something quite different. Maybe this would be negotiable, but I didn't go that way. And the GTA engine that many of, I think, researchers used was not available at the time, and probably still not for commercial applications. Here is a software architecture that we decided to go for a multi-process architecture for a simulation system. This was just to better use the multi-CPU systems of today and multi-GPU systems that you really need to guarantee some quick response and quick or good performance. There are two types of process: the rendering process that has this 3D window, and the GUI process that the user can use to control some functions. And all the actual functions are realized as a plugin. So this is kind of basic software architecture that we went for. So this is how it looks. Here we have some 3D overview for user that can observe how the testing or some scenario is going. Here is the GUI where you can control the vehicle speed and steering. Here are simulated fisheye cameras, and this simulates the responses from ultrasonic sensors. I think now I will play. Oh, this not mentioned our toolchain also. We have on Windows, we use Visual Studio 2015 and C++. Our assets, we are not 3D modelers, so we purchase most of it. And as I said, we do not really need it to with the best quality and with correct variety. I hope this will now work. No, so I have to play it from far. So what I want to show now is an actual test case scenario where this data was simulated into the ECU through the hardware, and this is the output of the ECU. This is what the driver normally sees. So now the car drives in the street, searches for parking slot. There is a recognition of parking lines from the video detected. So it detected an empty parking slot, and now it simulates some input from the driver, and the ECU will now actively steer the simulation into the parking space. This all happens automatically, and really the control inputs are coming from the ECU under test. We wanted to bring the whole setup here, but given the 2 flights of stairs and the weight of the rack, it was not possible eventually. I have one more that's already speed up. This one was based on cameras, and this is based on ultrasonic sensors, which is something you can tell that the target position will be aligned according to the slanted vehicles. It will not be perpendicular to the sidewall. You can see that these sectors here are linking, so this is what normally happens in the car when you cross an obstacle. So, perfect. So this was fast. Okay, we are good on time, so I would like to quickly go through some sensor models that we developed, or these two that you saw in action previously. First thing is a fisheye camera. This is the real camera. You can also see it on the demonstration there, stand there. Think about it, it has 120 field degree of view, so it actually sees more than perpendicular to the lens. It has 1.2 megapixels and output format some kind of IOV. So this is a test setup we did in our garage with some dummy obstacles with a special pattern on it. We did the same obstacles in simulation. We modeled the same cubes, and these should, with the same parameter setting, should give us correctly the same video output, which was very validated that they give. Not only this way. So we're going to challenge is in creating a fisheye camera model. So first of all, it's highly nonlinear, which doesn't go very well with the GPU's linear pipeline. It's all based in linear algebra. And this was the biggest issue. It has to respect the lens model so that we get the same outputs based on the same inputs that we compared in the previous slide here. So we have to use the same or respect the same lens model that's being used in production and in the real cameras that are being made. And we also need to convert the RGB format to the YOV format that's expected by the ECU for video streaming. So this is nothing that complicated, but you still have to keep in mind that we have to do everything in real time. So we have to find some optimal ways. So how to solve this problem? We have to linearize it. So for fisheye rendering, we did an approach when we rendered 4 views actually from the point of the camera. We rendered 4 viewports, or 5 viewports, sorry, one in the center, one looking 90 degrees to the left, one to the right, top and bottom. And then using some special or custom shader, we distorted in a shape that respects our lens model from the previous slide. This is the real output image from the camera, and you can see the 5 cycles here. These cycles being really on the same level as the front bumper, and they are still visible in the image. So you can see that the field of view is really wide. This is nothing I made up. I found it on Stack Overflow, but the implementation was not so straightforward. Here, this is more technical and more specific. How we proceed is first we render this in the DirectX realm, then we switch it to CUDA, where we perform the RGB to YOV conversion. Then through shared memory, we go to our hardware interface application, which is LabVIEW in our case, and we stream it to the real hardware through some software and hardware interfaces. So we had to optimize this whole pipeline to be fast enough, really. The whole data flow is 280 megabytes for this project. Second, but this is all technology now. For the future project, it will be over 1,000 megabytes per second. So this is some amount of data if you need to generate and stream it in a steady situation. Of course, you can multiply all the required operations if you have 4 cameras on a car. But really the biggest delay is in the 5 scene passes for every camera for rendering the texture cube when you need the 5 perpendicular cameras. So now there came this magical piece of hardware, RTX 2080, that should allegedly have a multiple viewport support for rendering. Has anybody of you played with this device already? Put your hands on it? No? I was hoping for some information, but I have to find out. Probably I saw it only in the NVIDIA presentations. I don't know, nothing closer. Okay, now I think we go for the ultrasonic sensory system, how to simulate ultrasonic in 3D gaming engine. Some basic on the sensors itself, that they transmit just a burst of ultrasonic energy and they receive it. So basically the most important thing is the time between the transmission and time of reception or some reflection. This is really nothing very, very complicated, or in this generation at least. You just ring the bell and you listen and measure the time when it comes back. Important thing is that there are 2 measurement modes, direct and indirect, which means that when this sends out energy, it's also perceived by the neighbors. So you have to also consider this transmission and this reception here, not only from this one, but also it goes between the neighbors. So the challenges is that sound is not light, which is what we simulate in the 3D engine. So we have to come up with some tricks how to treat it. And this sensor is not sensor model is not really perfect in the implementation. The proper approach would be to ray tracing and to shoot out really the amounts of energy, bounce it off, which is what happens in reality. But of course, you don't have the processing power to do this in real time. So there are some situations that can happen, like transmission from one reception to the other, or multiple receptions from multiple different targets within the field of view, or the multi-path reflection that you send it here, bounces over here, and comes back here, which is something that's really not possible at this point with 3D engines. I think again the solution could be the magical new NVIDIA card with a ray tracing demo, but I don't know. Probably I have to test it first because nobody has done it here. I only saw the videos from, what was it, Battlefield 5. They do the multiple reflections on the other objects. Okay, and here is an implementation. We of course use the depth camera for getting the distance of different objects. You can see there are 12 different cameras in the points of the bumper where the sensors are looking outside. So front side camera, front side sensor will see these traffic cones. Let's say outer left, it's somewhere here, and you'll see the road barriers. So we create a depth map from every sensor. Then we again go into CUDA space, and using some, let's say, 2D functions, we find or we search for local minima or some other patterns in the depth image that we then pronounce are the ultrasonic echoes. What you can see here in green, or you cannot see maybe from the distance, is the reflected target. So here, I think this is the right side, right, which is the bumper of the vehicle. So this is what we will simulate to the ECU on the test. Here are some numbers in distance. So I think it works well with the time. So this was some brief introduction or brief overview of the simulation systems that we are developing and we use in everyday testing. It's been really used in production testing, so it's not only some toy or some experiment, and it seems to have a future. Say something from practice, even the car manufacturers, the OEMs, are more and more interested about simulations, about virtual validation. And I think it's definitely one of the future areas that will be largely developed. Of course, we're not the only one. There are some companies providing these services commercially, but it was shown that if we have the information about the sensors via the manufacturer, we also know very well how to simulate the inputs for it. So there are some synergies, and it seems that makes sense to develop such a simulation ourselves. And this is well, okay. Again, this is all for my presentation. Share some questions.
I have a question based on the demonstration of the boss tracks, both on this print and in your presentation. The system itself looks very impressive, but since you're using also cameras, and also I think it applies to ultrasonic signals, the input is quite different from reality, right? Especially in this system, it seems that the input is is almost ideal in the sense that you have high contrast lines on the concrete. I assume that the LiDAR or the radar sensors are going to get perfect responses every time. How do you handle this when you need to transfer it to the real world, where everything is low contrast and you have a lot of noise and imperfect reactions?
Okay, this is what I try to explain with the functional testing. So in this scenario, in this kind of test, we do not really care about the performance. We do not care about low light conditions. We do not care about contrast. We are testing the whole system functioning together and performing the end user functions, because there are so many levels where it can go wrong. So we try to put in the ideal inputs. So we do not make it hard to detect the pedestrian, because this is easily detected. These lines are obviously perfect because it's just white line or some black background. But we test we can test the software integration, and okay, the car parameters in the control unit are properly configured. So these are the tests that are tested here. What were you asking is tested isolated on the level of algorithms. So this is where we use software in field testing, for instance. Then we record a batch of real world videos, and then we play it to the algorithm, tune it, and then play it again and see if it's improved or not. So this tests the whole system, providing ideal inputs, but we cannot test the performance or KPI on this.
How much time did you win between the previous way and today? Like, in terms of scale, 10 times faster, 100 times faster than the previous situation by using these virtual realities?
But I got the testing. I got.
How much did you improve?
Yes, I got the estimation from testing that 80% of the test cases can be carried over to simulation without impacting the performance. Full validation was, I think, 3 weeks. So 80% out of 3 weeks can be moved to bench testing, which is a lot of time. A lot of time is money. And the important is, of course, in run overnight unattended.
Okay, your software passes this test. What are the next steps before, next tests before this update will be shipped to real world?
When it's shipped to real world, there's always a full testing, they call it full validation. All the test cases are executed in the real vehicle before it's shipped to the real world.
Okay, so will be only driving, there are no automated tests after this test?
No. This can be used for some variant testing, but on a single car variant, customer will, at the moment, they still want to see a full performance of the system in a real car. We can test maybe different variants. So this ECU, the system goes, for instance, into E class, A class, I don't know, some 10 other classes. So we can test on E class with a full vehicle tests, but maybe the other classes of vehicles can be tested only in simulation.
And once you have done these virtual tests, and because now you have succeed to implement some algorithm and you be successful on the implementation to the sensor, the way you calibrate them, how much you reduce the success of implementation in real world? Like before there was a lot of rejection, now it's, what is the rework on the virtual test to make a real world validation? You understand?
Sorry,
It goes from the virtual test, then it goes for the real test.
Yeah.
And then the real test have failures. How much you reduce these failures, and how much you have to rework compared to previously? Because this is not only about time, it is about success, right?
Yeah, sorry, I cannot really, I don't know how to answer this because I developed this tool and this actual testing is not my thing really.
So you don't have feedback from the actual comparison between what is actually implemented after your virtual test?
No, from the real testing, I have no feedback. I of course get feedback from regarding the sensor models, how accurate is it, or we take traces in car, we take traces from the simulation, we compare it, we try, of course try to make it more alike. But what is the actual impact on the testing or rejection or let's say opening ticket to software from testing on the car or simulation? Sorry, I don't know this.
So you don't improve according also to the real test, to the real world test. You don't improve as well these kind of aspects. The transaction between virtual test, and real test accurate or less, and then re-improving the virtual test in order to actually minimize this success.
To ask the difference in
Yes, exactly.
password, okay.
Because you save a lot of money on virtual, but in reality you have to reduce that. You can do it by improving actually your virtual test. So the feedback from real tests will actually be more efficient in the next iteration.
I'm sorry, I really don't have some snow figures. I know isolated cases where it does not work here or works in the field or the other way around, I guess. But I have no sums here, no figures.
For the future steps of this tool, do you plan to make it more realistic in order to test the resilience to noise as a discussion was? Is it the next step, or what is the next step?
Well, actually it is, because the computer vision teams said, hey, it's a nice tool, what you've got here, but we wanted to make it look better. You don't need it in real time, so you can slow it down and you can generate some data for us. And this started, I don't know, in summer last year, so we're now making first, let's say, experiments with the actual computer vision teams that do the recognition software. This is now software in the loop, no more hardware. So yeah, definitely it's a way to improve the visual quality. And also use the same tool in different places or different parts of the development process. But of course, these people are also looking at other providers that offer much better realism by default.
But it's not just about like how beautiful we did the picture. It's just that if you're using a real camera in the real world, it will be disturbed by, I don't know, some leaves flying, some kids running, and it's very different from your ideal world you've built so far. And I feel like right now you're testing in the very ideal situation. So it's like you're capturing maybe 1%, the easiest percent of the whole possible situation. And I was thinking, maybe the next steps of this simulator would be to grab a little bit bigger chunk of reality and go harder and harder and harder until you get 100%, let's say. Because the more your simulation covers, the less real costly test you have to make in reality, right?
I'm surprised that you don't use even basic techniques like bumping or mapping of textures, which are like more realistic and moving to different weather conditions. Now, the idealist way is to actually play a real field, and then implementing a virtual perception of this reality, because you can create the 3D video capture. It's just simple photos, actually. So you create the 3D according to the photos that you have taken, and therefore you can match actually a real film and a real vision, and you don't make any more 3D modelizations, but from the video you create 3D, and then you test. That's, I mean, I hope it makes sense. I don't know.
Yeah, I know what you mean, and this is actually everything that will be shortly testing with the captured reality software that we generate the 3D scene from many photos, and it looks great.
Yeah.
But so far we had a real-time constraint, and this simple scene has tens of millions of polygons. So
no, you have a video, and then after you create the 3D, which is from the video.
yeah.
With several cameras, you can create actually a very simple camera. You can create 3D. Right.
Yeah, you can, but the models I've seen are very, very complex and very detailed so far. So they're not fit for real time, no?
In fact, you need to make core points for the 3D. What is important is the reaction on the images, because you have optical system. So if you don't show the reality, then your problem of testing is amplified, maybe. Because you must go back to the reality each time. You have to take the reality as an initial input, not as a virtual input. I mean, sorry, it's just like.
Let's keep that for the discussion, because we have other presentations, and maybe these presentations might bring some light to the questions that you are asking as well. Thank you, Andre, and let's welcome on stage.
So good evening, everybody. My name is Karel Surman. I'm from Czech Technical University, and in contrast to the other speakers, we actually don't have any autonomous self-driving cars. We are not trying to develop any self-driving car, but we are just playing with some kind of data and doing some stuff. So today's talk, I prepared it like 2 hours ago. It's still unfinished, but I try to make it to be interesting for everybody. I was told that I should expect something like mixed audience, ranging from people from research and development teams in Valeo and self-driving cars, all the way down to the game developers and other people. So I will try to say something which I hope will be useful or interesting for everybody. And yeah, so first something about me. Okay, so that's me, a little bit younger, without beard. I'm working at Czech Technical University. Recently, I spent some time in Catholic University 11 as a postdoc. And I don't know, I did something, I got some grants and papers. This is something just for the introduction. So this is something we did like 10 years ago during my stay in the Catholic University in Leuven. It is not self-driving car, but it's the result of the car with 6 roof-mounted cameras, or maybe 9, okay, 9 roof-mounted cameras, like that. And it was project from the Belgian government. And for some reason, Belgian government did not know where they put the traffic sign. So the project was find all the traffic sign in the city and provide the GPS location of the traffic sign. We were quite good, but it turned out that some traffic signs are already hidden in the trees, and we can't detect them. So finally, they just hired the people who ride the bicycle and just went through the city and look at the suspicious parts of the trees and discovered all these traffic signs. So it was just for introduction. So the outline for this talk would be like, I would like to spend explaining what is deep learning in 10 minutes for people who don't know it. I guess that there should be some people like that, otherwise I'm screwed and the presentation will be shorter. So who is here anyone who has some experiences with deep learning? Okay, so it's like 20% of people. Okay, so that's good. So I will say something about deep learning first, and then I will try to mention several cases in which I believe that the simulation and computer games might help a lot to do the stuff which we do. And what we do is basically computer vision and recently a little bit robotics. Okay. So to explain what is deep learning, at least for us, I will start by mentioning some problems we are solving. So one of the typical, or many typical problems in our field of study can be formalized as a search for some kind of function which solves it. Or if you don't like function, you can say algorithm. So one of the typical cases is that you've got camera image, and you search for the function which takes this camera image as an argument and maps this camera image on another image which has the same resolution as the original image but contains the label for each individual pixel in the input image. This task is usually called something like semantic segmentation, and the color in this picture encodes the labels in the original image. So this is there are several types of these tasks like detection and tracking and so on. So I would call it like scene understanding from RGB or maybe RGBD if you have some depth sensor like LiDAR. And if you find such kind of function, you can then run it, and this function provides you these output pixels, which helps you to understand the scene around the car usually in real time. Another type of problems we are working with, or we are trying to solve, is typical problem from robotics. I would call it something like motion control from RGB or from RGBD. So, for example, in this example, it is grasping of an unknown object by a manipulator enhanced by camera. So, and the task again is to find a function which takes the RGB images from the camera, which contains the workspace of the robot, and maps this image directly on the joint torques. So there would be something like 10-dimensional vector of real numbers, which controls the torques in particular joints of this robot. And we search for the function which pulls the trajectories of this robot, which successfully grasp the object in the scene. Okay, and you can actually learn it. Okay.
And succeed only rarely. Each day they live.
So, in both of these programs, we search for the function, and we have to somehow specify it. So, by searching for this function, we usually have some criterion. So, in this scene understanding programs, the criterion could be simply number of wrongly classified pixels. In this motion control programs, the easiest criterion for is something like number of unsuccessful grasps of the object. And then, if you have this criterion, you have specified what you want. You just want to learn this function f, and this learning of this function is usually formulated as a gradient minimization of this criterion function. It turns out that it does not matter, that the particle optimization method does not matter that much. But what matters is the structure of this function. Whether you use linear function, exponential function, or some really complicated function, and what kind of data you use. Whether you have enough data which captures the variability of the whole board in which you want this function to operate and so on. So this is something which I will now speak a little bit more about. So the first of it is the structure of a function. It's to find the structure of the function, we have to go something like 60 years back, 62 years back already. In this year, people has developed a device which is called tungsten electrode, and this is a device capable to record signal from a single neuron. 2 years after that, Google and Wiesel took this electrode and designed the following experiment. They fixated head of anesthetized, paralyzed cat into some clamp and forced it to look at some projector on which they projected different images. And they connected this electrode into the cortex of this of the cat. It's like part of the brain which is responsible for processing of visual information. And they connected it to a single neuron. And then they observed what kind of visual stimulus caused the change of the signal in the neuron output. And this is how it looked. And this is what they have heard. So what you hear are the inputs of this neuron, this electrodes, which are just transferred to the audio signal. Interestingly, they did not know what to show to the cats, so they tried many different images. They started to show the cat animals, humans, and naked humans. Then I guess checked the genitalia, and in the end they were like desperate. Nothing worked, nothing fulfilled. So they were about to give up. They switched off the projector and standby pattern, which kind of looked like that, appeared. And in that time, the neurons started to have very strong responses and started to fire like that. And this is something which really happened, also not only on the cat, but also on the monkeys and other animals in which they tried. And it turned out that these neurons are very sensitive to something like oriented edges in very local places in the visual field of the animal. Surprisingly, they've got Nobel Prize for this animal torturing in 1981. The results of these experiments, there were several of them, was that the cortex structure, the structure of the brain of this neuron, do something like it's something like concatenation of many simple nonlinear convolution functions, if I say it really simply. And that's basically what people call deep convolutional neural networks. If you know what is convolution, then you can imagine that you just concatenate several convolution function and you interleave it with some nonlinearities, and that's it. If you don't know it, it's just some kind of function which does something, it has some pre-parameters and so on. And they also found out that these neurons are very sensitive to edges and orientations. And people from computer vision try to use the same structure of the function of this function, the deep convolution neural network. They tried in 1990 in 100 images, and it didn't work. It did nothing, and people were disappointed. So they tried like 10 years later on 1,000 images, and it worked, but it worked only on handwritten zip codes, like for recognition of handwritten numbers between 0 to 9, but on other complex objects, it didn't work. And it took like 14 more years, and people tried on 1 million images. It took like a few weeks on few GPUs, and it yielded a function which worked much better than anything else. Here you can see what happened. So this is the results of the competition. The lower the better. Here are the years. Here's the performance. Classification error, and in 2010, 2011, the results were almost the same. It suffered somehow from diminishing return. Then they finally learned this cat structured function on 1 million images, and something happened. It's like there was a huge jump, and since that time, people are tuning the structure, and they have been able to achieve better results than humans in the end. Another interesting thing is that without any enforcing of this second stuff, that the neurons should be sensitive to edges and their orientation, they visualize the patterns on which the neuron in this learned function were the most sensitive, and surprisingly, it happens the same. So these are the patterns on which the output of neurons in the first layer of this deep neural network were having the highest responses. These are basically oriented edges or some chess-like structures, or maybe some like color gradients and so on. This is what they found out in the second layer. Like more complex patterns, but still it's like edge-like or maybe circle-like and so on. And deeper you go in the neural network, the more complex pattern appear. Okay, so that's like what kind of structure people finally started to use. And it seems to me that it works now. And the other problem which we all are trying to solve now is how to get the sufficient amount of training data for training this neural network. Because 1 million annotated data is huge amount of work which cannot be done easily. So to summarize, the machine learning, so deep learning is something like a set of machine learning algorithms which estimates parameters of deep convolution neural network to minimize some kind of loss on some training data. And it turned out that this deep learning works, but it's extremely data hungry. Annotating costs for single image like that to provide annotations, pixelized annotations like that cost between $10 and $20, depending on the nation of people who are actually creating these annotations. But it turns out that also the quality of annotations are strongly correlated with the pricing.
Grasp object.
Yeah. And this, so it's about like for this scene understanding problems, like the semantic segmentation, you can do it. You can pay a lot of annotators. That's what companies actually like Valeo are doing. They hiring a lot of annotators, and they are annotating millions and millions of images, and finally they've got like huge data sets on which they learn it, and it works because it has already seen almost everything which can be seen on the real world. And in this motion learning problem, motion control problems, is much more complicated because for this case you cannot get some data set and then work with this data set in your computer. You actually have to use some kind of hardware. So for example, in this grasping of objects, they were able to do it, but they were able to do it because Google bought 16 same manipulators to parallelize the learning process, and they were learning it over several days. And also it was possible because they were able to do the self-supervision. They have been able to automatically decide whether the grasping was successful or it was not successful. Otherwise, there would have to be a single person for each manipulator saying, okay, it was okay, no, it was wrong, and so on. In some problems, it is not that easy to build a system which has this self-supervision. So it's another types of task in which I believe that games or simulators might help a lot. Yeah.
Why they didn't choose just some system which is touchy instead of pressing?
Because they want to learn the system to grasp it and
Yeah, but I mean, the point is to make a accurate machine learning regarding this identification.
well,
The grasping itself is a mechanism.
no. They don't want to do the identification of this object, but they want to learn a function which accepts the image from the camera and directly maps this image to control signals for this manipulator. And this manipulator could do different things. It could just touch the object, but the grasping is quite complicated because it depends on the size of the object, on the homogeneity of the material, the softness of the object. So basically they choose it because it's challenging. It is known to be challenging, so they wanted to show, okay, that's something other people are not able to do and we can do it. So, okay, so as a result for me, the cheapest way how to do it is to train on sufficiently realistic game or sufficiently realistic simulator. And that's what everyone is trying to do now. So I will first say something. How long time do I have?
Yeah, you can still go on.
Okay, so if you get bored, just let me know or just start drinking the beer and it will be the signal for me to. Okay. So the first thing is using games to generate annotated training data for scene understanding problems. So you will see more about it, but what we have done is that we have participated in reverse engineering of this GTA 5 game. It's like AAA game, you know it. You can drive the car there. You can also shoot people there. That's what we don't do, but. And as a result of this reverse engineering, we can like switch on the autopilot, go home, and after 1, 2, or 3 days, we can have something like 1 million images. And not only the images, we can have also text. And we can also have something which is called stencil layer, which is something which contains the information about the type of the object. So we know which pixel contains the car. We know which pixel contains humans. There are so many humans here. There are some small humans. There is a human hand. We know which pixels corresponds to vegetation and so on. There are also some strange stencil layers like artificial light. So we know which pixels are influenced by this artificial light and so on. We know 3D orientation of all objects in the scene and so on. It is also interesting that we are able to influence several things. We are able to move the object. We are able to switch on the autopilot. We are even able to force the autopilot to go outside to the off-road driving and so on. We can influence time and night the cycle. We can influence weather. It's like extra sunny, clear, foggy, overcast, raining, thunderstorms. There are also some this shallow puddles. I don't know how to call it. Water. Which might be quite interesting. Also snowing, which is probably quite far from what we know to be snowing. It's like the game is probably from California, so there is not so much snowing. And that we observe one problem. Like good weather, if there is a good weather, there is enough people around, but once it starts raining, the people actually go away. So we have not been able to generate enough training data with people in the raining or so. You can do even like very crazy stuff, like there's a whole community of people around the world who just spend the time with creating something which is called mods. So there are, for example, publicly available tsunami mods or airplane crashing mods, stuff like that. Anyway, if you do it, if you generate 1 million data or maybe 200,000 of data, and you add this training data to standard training data sets, which is available in some public competitions, surprisingly, it helps. It helps a lot. So here you can see, so on easy cars, if you add 10,000 images, you've got something, the higher is the better. I don't know what is this actually. 65% accuracy. Here you can have something like 70% accuracy. On moderate difficulty cars, it's like cars which are usually partially occluded or hidden in the shadows or something like that, you can get these results. And on the hard ones, you can get this result. Obviously, the more complicated the situation, the bigger is the improvement. The thing is that these complicated situations like occlusion and so on it is impossible to generate all possible occlusions of all possible cars. It's like, or it is impossible to see all possible occlusions of all possible cars by all possible objects and all possible positions in the real world. So here it helps a lot. For easy cars, it turns out that if you have too many training examples from this, it overfits on this training data for GTA. So it works best on the GTA, but it stops, it even decreases the performance on the real world. But in hard cases, it helps a lot. And surprisingly, you can go even farther. So, for example, you can take like GTA samples, and you can again use some kind of deep learning in which you take this GTA image and you try to generate some real light image, which should be more like real images. The only problem is that you don't have real images which would correspond to the scene to the scene from the GTA. So there is a way how to do it. The way is called generative adversarial, and since there is very limited time, I will probably skip the way how to do it. But anyway, that's what you can do. Another thing, or that's something which I would like to say. So it's what we are recently doing is that we are also trying to build simulators of other sensors. So, for example, we have created something like 4 virtual cameras in this GTA, which provides RGB images and depth images, and we put this together to simulate the LiDAR. And this simulation of LiDAR is kind of ideal. It's like ideal 3D-point cloud, which is far from reality due to missing systematic failures like missing measurements on reflective surfaces like water, mirroring effects on glass, or multiple responses on trees, on leaves, or stuff like that. So what we do is that we've got some data set from Valeo, which has been captured by real LiDAR, and we are trying to use this deep learning to refine this ideal data set to something which is closer to reality. And well, this is some kind of preliminary results. So we are preparing with Valeo some data set which will be publicly available. There should be like images, labels, including the vegetation and so on. And there should be also some LiDAR data. You want already start to drink beer or? So another interesting thing is that we can learn this deep convolution network, which works nicely on real images, and then you can do something strange. So this is the result of the deep network for semantic segmentation. It tells you on which pixels are occupied by cars, and then you can artificially generate some really small noise. This is something like 1,000 times gained noise, and you add this noise to the image. And if you look at the output of the same network which worked on the original image, it doesn't work at all. Of course, to do this, to generate this adversarial noise, you have to have access to the images, and you have to have access also to the network, which is usually not the case. So it's one of the things we are recently working on. So maybe, okay, I'll skip it. And I'll jump to the very end. So I have mentioned that we don't have any real car, but at least we've got this robot. It's like that size robot, and what we do is that we try to control these flippers, these auxiliary subtracts autonomously in order to traverse the terrain well. And also in these cases, we had to build some physical simulator, and without this, it would not be possible to achieve this result, because generating or collecting 1 million trajectories with such a robot is impossible. First of all, because it would break after, I don't know, 1,000 trajectories. So that's very last thing. But something which might be interesting for people who works in who try to develop self-driving car. So this was the research which was motivated by newly emerging solid-state lidars, which have been announced by Energy company. These new solid-state lidars are promised to allow independent steering of the measuring trace. So basically, the idea is that if the car is doing emergency braking, you can just focus all the depth measuring rays just in front of the car and see how far you are from the potential obstacle. If you do the turning on T-junction, you would rather look on the sides or something like that. And the principle of this device, as far as I understood, is that there are there's a laser emitter, and the emitted laser beams are transmitted through something which is called optical phased array. This is something which can influence the direction of the laser beam, and you can just electronically control the optical properties of this optical phased array, which allows the ray steering. And once you set the direction in which the laser beam is going, the laser beam reflects from the scene and is captured again by some kind of camera or SPED array, and the depth is estimated from the time of flight. And what we try to do from this device is something between motion control and scene understanding. So we've been solving the following situation. Given the sparse depth measurement captured by this LiDAR, we try to learn some function or deep neural network which estimate dense 3D voxel map of the terrain. And also, given the current depth dense voxel map, we wanted to control the depth measuring rate in order to improve the map the most. I won't go into some technical details. I will just say that we have formulated the problem as a minimization again of some error or mapping accuracy, logistic loss between a reconstructed map and some ground truth map. again, in this case, it would not be possible. It was not possible to do it in reality. First of all, because we don't have this device, it is not yet commercially available. Even they are still promising that they will send us. And second of all, because it is complicated to do the experiments in reality. So we have to create some kind of like artificial simulator from some publicly available data sets, capture it by well-designed LiDAR and so on. And we've been able to achieve quite interesting results. So this is the input. These are the sparse measurements which have been captured by controlling the motion of this depth measuring cranes. And these are the reconstructed maps. So considering that these are like extremely sparse, we've been able to reconstruct some basic objects like trees or parked cars around the street and so on. And this is it. There are some results. So RGB is only just for visualization purposes. There are some sparse measurements. The red one is the position of the car, the global map, and these are the reconstructed maps. Maybe. And yeah, so that's the final map. Again, this is what we measured, this is what we reconstructed, and it is high resolution ground truth map. It's like not ideal, the trees are somehow simplified, the cars are simplified, these are the trees, but considering the data we had, it's kind of reasonable results. Okay, so it leads us to the summary. So I believe that simulator and games will definitely help us in many aspects.
Okay, so hello, my name is Tomáš Černý. I'm from company Valeo. So we started as the research project. We were doing some challenges, outdoor competitions with small cars. Then we moved into bigger car, which is today E40. And our goal now is to have the first robotic car. The picture is our team. Last year we won a competition and we traveled to San Francisco to meet Sebastian Trump. You might be losing. He's the guy who led Google Auto. So this is our car from inside. It's just a prototype. We got all known computer in the trunk. And this is our brake by wire. We hacked into the car. We sent commands over CAN, but the only thing that we weren't able to control was brake. So we had to put some sort of linear motion to control. Okay. Then we bought new hardware by NVIDIA. That was released a few years ago. It's this board. It's quite powerful. Our car is equipped with a few sensors. We got 6 cameras, one 90 degree and 5 120 degrees. We got radar in front of the car and 2D LiDAR. First, when we started the development, we wanted to do precise localization. We created a map, we localized, and we drove the same track again. This is an example. This track was quite small, and the car was driving around 30 kilometers per hour. It was so fast that none of us was able to drive it in that speed. Then we were thinking, what next? We know how to drive a car, we did some motion planning and these things, and we moved into more machine learning way. So we don't want to localize, we want to use machine learning, detect objects, create some sort of local map, and be able to move in the map. So we were started to look for neural networks that exist and we can use. So first network we found is used for full semantic segmentation. You heard of that topic in previous presentation. This network is quite successful, but
to drive a car, you need to detect lights. And it didn't know where the lights are. It knew very well where cars are, people, signs, no lights. Then we moved on and we found yellow. This network is really good for detecting objects. It detects 20 buses, but what we needed only cars, trucks, and people. It's what we found on our race. So the yellow is from GTA that I'm going to go later. Okay, then we were looking more and we didn't find a network that found lines. So we started to develop our own and learn. So we were trying to find some data sets. We found 2 data sets. It was Cambit and Cynthia. Cambit is manually annotated images. The Pro is, it has a lot of images because it's just 640 pixels wide. It's not enough. And then Cynthia, it's the dataset from computer game. They have a lot of different landscapes, weathers, but it's not futuristic. So we were thinking, what next? We learned something. It was working not really well. We tried to annotate our own data. It was very painful. I was doing some annotations for lines. It took me 5 minutes for one picture. So we said, no, it's not possible to learn. And we started to look for photorealistic simulator. We found out GTA 5. GTA 5 is really close to photorealistic. And when you use some modes, it's really good. Quite easily, you can get the buffer and stencil buffer from GTA, from the DirectX pipeline. Stencil buffer is the same picture as you see, but it's picture of classes. You can easily find there cars, people, some buildings, but the problem is you can't find lines. It's just some sort of picture class. So we were thinking what next. We looked into the textures and we changed them. So this is the same picture. This is from what gives you normal GTA, and this is our modified picture. We on the textures we annotated by hand. It was few hundreds textures. It took us few days, but the very good thing on this is you can generate a lot of situations. You can change weather, you can change daytime, and you just run it, record data, and you get data for nothing. When we started doing this, we were able to change the textures, but we needed to take the same pictures for realistic image and annotated image. So we started to get deeper into the GTA. We brought our own mode. We had DirectX device. We changed some virtual tables for methods, and we were able, in the end, to get 30 frames per second, one frame this, one that, and collect data. From that data, we were able to get lines, roads, and broken lines for our learning. So in the final solution, we use GTA Autopilot. It drives on its own. We put there custom camera, custom pictures, hack the DirectX pipeline, and recorded the data. We can record it as rollback. So this is how it looks when we record data. It's not really a nice thing to look at all day. The process to make it in this speed took us few, I would say, weeks or small number of months. Just in the end, we ended with 5 terabytes of data for learning. As I said, we were able to collect 30 frames per second. It's some sort of, I don't know, 2 million something per day frames. It was quite a lot. We created different landscapes, weathers, hours, and we started learning. When we learned, we found out that we can't process this data. So we have to read the scale. So we started to develop our own framework for reading data. I will be going to talk about that. So when we learned our neural networks, this was the final network we learned. It saw very well. The problem in GTA is that it uses a lot of effects to make it nice for eye. So you see a line very well, and in 10 or 50 meters, all the shaders applied to that, they make from the line just 2 pixels free. So we are upscaling the image, rendering in 4K, and trying different stuff to see it in the annotations. So it's photorealistic, but not really. It's more nice to eye. We wanted to know if all this works in the real world, because we want to drive our car in the real world. So we took our car and recorded some data. So you can see the video. This is network learned only on artificial data from GTA, and it saw really well. We were really surprised. The problem that still was there was sun. The sharp shadows make networks really, really bad. When it's sunny or no shadows, it's absolutely perfect. I will show you the autonomous driving of the car, our first test, when it was driving in picking lines. So, what we found out with GTA 5? We found out that it's a really easy way to obtain data. You can obtain it from different environments, from countryside, some dusty roads, from highways. You can create it in night, in day, in sunlight, rain, snow, and this is what GTA does really good. The thing is how to learn the data. Nowadays, I don't think no company is able to deliver good network on snow, rain, let's say sharp shadows, even not NVIDIA, probably so. We can transfer this network to real world. You saw it worked. We got no metrics, but from our eye, it was quite okay. And the car was driving also. We were also playing with some architectures of neural networks, but the most important thing is data. When we started, we got, let's say, few thousands of images. It wasn't enough. We are trying different architectures. It just was moving slowly, but then we added more data from different landscapes, different weather, and it was big difference. So data is core to learning. So now in the video, we were doing some simulation in GTA. We also use GTA as a simulator because we want to test our stack before we go on the lake. And we use the image for input as camera. We don't really care that it's not real. Our test is not to hit a car, not to get out of the way, and so. So in time, now we are developing remote control. It's something we believe is necessary for first AI cars. We got our station in our company. Car is connected to LTE network, and we can control the car remotely. Thank you very much. You can find us on YouTube if you want to see more, or Twitter.
Any questions?
You use GTA as a simulator. Do you simulate the sensors, camera as well?
We simulate camera. We don't need to simulate cameras. It's what GTA gives us.
So LiDAR was there.
Yeah, we simulated 2D LiDAR. We use ray tracing, but the problem with ray tracing is that it's slow. The FPS of GTA drops from 40 frames per second to 10 or 12, I believe. So we want to use camera that we will take one row from that. But there's a problem that if you use multiple cameras, you linearly slow the pipeline because you have to render for one camera, second camera, third camera. So we can simulate 3D LiDAR from that, 2D LiDAR, but with every device we put there, it gives us linear slowdown of the simulation. Now we can keep real time with one camera, but if we want more, and we will have to go out of real time.
Is it easy to inject in GTA and simulate the sensors within this game, this game engine? If it's easy to inject in this game,
It's a
yeah.
It's not hard when you know what to do. Now I believe we will be able to do it really quickly with another game. But the thing is that when we started, we didn't know if it's even possible. No one did something like that before. We know we can get some sensor buffer. We didn't know if we can change the pictures. Changing camera is very simple for or getting that much, but changing of the textures, it was the harder.
Actually, it takes a few months.
Any other question? Because I see there.
Just how you handle so huge amount of data.
Every computer has, for machine learning, has some rate. We got in Python some multi-threaded pipelines for reading data, making some changes to data, and then pushing to a GPU. It was a lot of work on this.